So in our lesson today, we're going to continue our discussion of graphing rational functions without a calculator. But today we're going to add in that they may possibly have holes. So yesterday it said we were graphing without holes, but today they may or may not have a hole. And so we're going to talk about how we'll figure out whether or not they do and add that to our list of things that we need to use in our steps. But our steps are pretty much the same. We need to find our domain, which gives us our vertical asymptotes. We need to use our rules to find our horizontal asymptotes. We're going to find our x and y intercepts, and we're going to graph the function. But remember that whenever we're talking about our vertical asymptotes, that we have to reduce our function first. And we haven't actually had any functions that would reduce. But when they do, then that is what's going to have an effect on whether or not we have holes in the graph. So let's take a look. We're going to factor out our function. So this is a difference of squares. We have 2 minus x times 2 plus x. In the denominator, we have 2 plus x. So our domain still comes from the denominator. If I set 2 plus x equal to 0, I get x equals negative 2. My domain is all real numbers except x cannot equal negative 2. And in the last few days, we've said, okay, well, that means that that's a vertical asymptote. However, in this situation, that x plus, or 2 plus x is in both the numerator and the denominator. So it does reduce. We can get rid of that term and divide it out and reduce this down to just 2 minus x over 1. When that happens, when it reduces out, it is not a vertical asymptote. So in this case, there is not going to be a vertical asymptote because that denominator went away and it divided out that only factor that would have given us 1. And the place where it divided out was at negative 2. That negative 2 is actually just a hole in the graph. Now, negative 2 is the x value at that hole, but we're also going to find the y value of the hole. So the y value of the hole comes by putting this number into the reduced form equation here. So 2 minus negative 2. 2 minus negative 2. So we get 2 plus 2, which is 4. The y value is of the hole is 4. So we get that by putting in reduced form. So to get your hole, put in the reduced form. Okay? All right, so holes and vertical asymptotes are kind of tied together because if it crosses out, not a vertical asymptote, it will be a hole. Now for the horizontal asymptotes, remember our rules. The top is larger than the bottom exponent, and so there is not going to be a horizontal asymptote. Well, so it's beginning to look like this one is going to be kind of strange because most rational functions have a vertical and a horizontal asymptote. This one doesn't have either one of those things. So that's kind of interesting. So let's see what happens. So we're going to go ahead and do our x-intercepts. Remember, x-intercepts come from setting the numerator equal to 0. Now you could do that in the reduced or in the original form, but we'll use the reduced form. So 2 minus x equal to 0. So x is 2, positive 2. So 2, 0. For the y-intercept, we put 0 in for x. So if I go back here and put 0 in for x, or here, 0 in for x, I'm going to get 4 minus 0 over 2 plus 0 gives me 4 over 2, which is 2. So I get the point 0, 2. Oh, sorry. 0, 2. All right. So it looks like we just have a bunch of points. We don't really have any asymptotes to graph, so let's just graph the points that we have. We have the points 2, 0, we have the point 0, 2, and we have a hole at -2, +4. And when I say a hole, we're going to make an open circle there. Move that over just a little bit. I think I got that off just a little. All right. So these points that we do have here look like they all line up. And they do. So I'm going to find me a little straight edge here and draw in this line that we got. Now this line that we got jumps right over that hole. Now if you were to type this equation into Desmos or into a TI and graph it, it's going to look just like a line. You won't see this hole unless you zoom in a lot on this little point right here. And then if you zoom in enough, you'll see a gap in the line. So what's happening here is that it just takes on the characteristics of what was left in the numerator. This is the graph of the line 2 minus x. Remember how to graph a line? You go up. This is -x plus 2. Y equals -x plus 2. So you would start up 2 and then you go down 1, right 1, down 1, right 1. You remember that? So we get this line, which is exactly the same as this. The only difference in these two things is that this one has a little gap, this one does not. Other than that, they look the same. So if my equation had reduced down to like a parabola, if this had just been an x squared that was left over, it would take on the characteristics of that parabola with just a hole in it somewhere, wherever this point was. So look for that. If the denominator totally goes away and there's no vertical or horizontal asymptote, it may just take on the characteristics of a function that you already know how to graph. All right, so that is a possibility. So let's take a look at our next example here. In this example, they've already factored it for us, so that's kind of nice for most of these things. It looks like we have one of these terms here that is going to reduce out. But remember that even though it reduces out, when we're looking at our domain is still x cannot equal -4, -3, or +1. Now the one that reduced out, that one is going to be the hole. So there is going to be a hole at -3. But the other two that did not reduce out, those are still vertical asymptotes. So I still have a vertical asymptote at x equals -4 and x equals 1. So don't forget that you could have asymptotes and holes. Only the ones that reduce out are going to be the holes. All right, for horizontal asymptotes, we need to think about what this would look like if we multiplied it all together. Really just the highest powers here. So x times 2x times x would have been 2x cubed. And in the denominator, x times x times x would be x cubed, plus a bunch of other stuff out there, but that's really irrelevant because we would be needing to use the coefficients in front, 2 over 1, so our horizontal asymptote is y equals 2. All right, now for x-intercepts, we're going to use the reduced form to find our x-intercepts. Set these top pieces equal to 0. So x would equal -2, or 2x equals 1, and x is 1/2. So -2, 0, 1/2, 0. And then for our y-intercept, we're going to put 0 in for the x's. Again, I'm going to use the reduced form. It's just fewer places to plug into. So I have 0 plus 2 is 2. 0 in here, minus 1 would be -1. 0 here would be 4. 0 here, -1. So I have -2 over -4, or +1/2. So 0, 1/2. All right, the only piece of information we have not found is the value of the whole. So remember, we're going to put into the reduced form here as well. So I put -3 in here. -3 plus 2 is -1. -3 in here would be -6 minus 1 is -7. -3 here would give me +1. -3 here, -4. So I end up with 7 over -4. So -7/4. All right, so we have all of our information. So we're going to put this over on the graph. So we have a horizontal asymptote at +2. A vertical asymptote at -4. And a vertical asymptote at +1. We have a whole at -3, -7/4, so that's 1 3/4. So -3, -1 3/4. We have a whole. We have an x-intercept at -2, another x-intercept at 1/2. We have a y-intercept at 0, 1/2. So that looks like in the middle section we have another one of those kind of offset looking parabolas. So we have to join all these points together. So good news is you don't have to do any test points in that section. So we just need to test out points for the outside pieces. So we're going to have -5 for the left-hand side. So if I put -5, we're going to put in the reduced form. So -5 plus 2 would be -3. -5 in here is -10. Minus 1 is -11. -5 here would give me -1. -5 minus 1 is -6. So I end up with 33/6. So 33 divided by 6, that's 5 3/6, or 5 1/2. So this gives me 5 1/2. So at -5, I go 5 1/2. 1, 2, 3, 4, 5 1/2. So I get a curve in the top section of that portion of the graph. Now I also want to test something over here. So I'll just do 2. So when I put in 2, 2 plus 2 is 4. 2 times 2 is 4, minus 1 is 3. 2 plus 4 is 6. 2 minus 1 is 1. So I have 12/6. All right, so we get the point 2, 2, which gives us another problem, because that falls on the horizontal asymptote, which is possible, but we still now don't know whether it's coming from the top and then coming back down, or from the bottom and coming back down, or from the top and going back up. So one more test point. So I'm going to do this down here below. We'll put in 3. So when I put in 3, 3 plus 2 is 5. 3 times 2 would be 6, minus 1 is 5. 3 plus 1 is 7. 3 minus 1 is 2. So I get 25/14. Well, 14 will go into 25 one time with 11 left over. 1 11/14. Well, that is a little bit below 2. So I'm a little below the line. So here's what that means. I have to join these points together, and I have to approach the asymptote. So it just comes back up from the bottom towards the asymptote. Also, I have to cross through and approach the asymptote that's vertical. So it still is a curve in this top section, but then it comes up from the bottom towards the asymptote that's horizontal. So some different things can happen in these graphs. This one has just about everything. It's got a hole, it's got vertical and horizontal asymptotes, it crosses the horizontal asymptote right here. So about everything that could happen happens here. But in addition, remember that some of these graphs of the rational functions aren't even going to look rational, because if the denominator divides out and I just get a polynomial function, it's going to look just like the polynomial function with a hole in it.